Yeah, so let's do part two, and add to the demos that I've done so far, and have more examples of me working at the heat engine stuff. That's really, the reason we cover thermodynamics, even though many of you might have seen it in your chemistry classes. I think in chemistry classes they don't emphasize heat engine cycles as much as we do. So, they care more about stuff like enthalpy and all that. I don't even use the word enthalpy except just now. So let's get started. I hope I don't get one of the two questions I've already done. That way I can, yeah, this is not one of the two questions I've done, I think. Yeah, the other one had some graph there that I don't have. So, all right. First law of thermodynamics gives a statement with the quantities involved. Yeah, all that. Imagine a monatomic ideal gas undergoes expansion. Oh, yeah. So let's sketch it out. That helps me think through the scenario and not make mistakes. So the first step, almost always in thinking and analyzing thermodynamic processes, is drawing a PV diagram to visualize the changes that are occurring. So I'm given that a gas is at some pressure, 105 kilopascal, and it's starting from some volume. Let me say 5 times 10 to the minus 4 meter cubed to 17, not to scale, 17 times 10 to the minus 4 meter cubed. And then it's not describing change of pressure, so, and it just says at a pressure, so this is probably the process. Good? So it says calculate the change in internal energy of the gas, heat transfer into the gas, and work done by the gas. Internal energy is easy. Let's make sure I know what type of gas. It said monatomic. And monatomic is important because that implies the internal energy is given by 3/2 NKBT. And I'm going to use this expression to replace out of ideal gas law, which says PV is equal to NKBT. So I can replace this NKBT with the left-hand side of the ideal gas law. So I can say the internal energy is equal to 3/2 PV. So, all right, I think I have all the numbers to plug in. That's the internal energy. So the change of internal energy is, change of this, change of delta PV. Here pressure remains the same, so it's going to be 3/2 P times change of volume. Let me do this in Wolfram alpha. Yeah, I think I have all the numbers. 3/2 times pressure, 105 kilopascal, times the change of volume, which would be 12E minus 4 meter cubed. I did a difference in my head. It's quicker. 189 joules. 189 joules. Good. Now Q, I can't quite calculate it directly. Really, for this process, referring to the first law, easiest thing to do is find internal energy change, work done, and from that calculate Q. I can say Q is equal to change of internal energy plus the work done by the gas. So let's calculate the work done by the gas. That's pretty easy in this case. It's basically area of this rectangle. Or, I guess this is work done by the gas, P times delta V. P is the height, delta V is the width. So here, in fact, I already have P times delta V, just get rid of 3/2. That's my work done, 126 joule. And heat transfer from this expression here is the sum of these two. Oh, I think I can do that in my head. 315. Hopefully I did it correctly. Considering the same initial conditions as in A, so let's copy this over, and I can reuse some of the stuff. This time it's B. If the expansion occurs isothermally, I don't think I can use a lot of the stuff. So let's do isothermal expansion. That actually gives me an easy answer for change of internal energy, because no change in temperature means no change of internal energy. And whatever I calculate for work, that's going to be amount of heat. So let's work that out. I think I can still keep a lot of the stuff. I just have to draw a new process that shows isothermal expansion. So isothermal expansion looks like 1 over x graph, because that's the curve that will keep the temperature the same. So it'll look something like this. So, this is almost 3 times the volume. So the pressure will have gone down by almost a factor of 3. I can calculate that. Or maybe I don't even have to calculate it. So I have a feeling I'm gonna make use of ideal gas law, so I'll keep it for now. Let me erase this part. So the work done here gets a little bit more complicated. I have to do an integral. The work done here is going to be integral from initial to final of the infinitesimal work done. So let me write that out. I have infinitesimal amount of work done, which is going to be at a given pressure times the infinitesimal volume change. And I'm going to integrate this from the initial state to the final state. From the initial volume to the final volume, which I conveniently have. So I'll just keep everything that way. Now, I do need the pressure as a function of volume so that I can actually do the integral. For that, I'm going to use the ideal gas law. I can solve this for pressure. Pressure is equal to NKBT divided by volume. And I think I'm going to use one more simplification after doing the substitution. So I have pressure is NKBT over volume times dV for the integral. And I'm never given a temperature, or in fact, I'm not given any of these quantities, N or T, separately. So what I think I should do is I should use this identity equation, the fact that initial pressure times initial volume was equal to NKBT, and throughout the entire isothermal process, the right-hand side doesn't change, so I can just replace it with this constant left-hand side. So if I do that substitution here, then the numerator simply becomes initial pressure, which I have, times the initial volume, which I have. So let's do the integral. Let me factor out the stuff that factors out of the integral. Pi times Vi. The integral of 1 over V is the natural log of V. It's one of the integral formulas you used to have memorized. Integrated from Vi to Vf, those are my limits. So just quickly working this portion out, it's technically ln V final minus ln V initial. With the help of the logarithm algebra, I can rewrite this natural log of V final divided by V initial. That makes things nicer, because then I don't have to figure out what is the natural log of meter cubed. Meter cubed cancels out. So the answer here should be Pi times Vi times the natural log of V final divided by V initial. This should be the work done by gas. So let's write all this out. Let me just copy this over for the parameters. I just don't want to scroll back and forth. Or I guess I already had some of them here. So initial pressure times, this is initial volume, would be 5 times 10 to the minus 4 times meter cubed times natural log of V final. I'm just gonna type in the part that won't cancel out. 17 divided by 5. 10 to the minus 4 meter cubed cancels out. So when I do that, I should get answer in joules, 64.25 joules. And it makes sense. The area here would definitely be smaller than area here. So 64.25. So 64.25. And as it's doing that work, it can afford to have no internal energy change, even though, the first law says this, because there's a heat transfer, exactly enough to balance it out. That heat transfer is what makes the process isothermal, really. So, all right, so that's the process. Finally, physics demo called the fire syringe, where I love this. Based on the information you see in the photo. What? How much time do I have? 9 minutes. All right, I guess that's enough. So I gotta know the compression factor. So let's do this. You can just eyeball it. It doesn't have to be very precise. So so this is my work for C. Oops, that's not the color I wanted. The main thing I need to know is compression factor, ratio of V initial to V final. So, and I can use the ratio of the height of the column, I think, as the cross section probably remains constant. So let me get this as a measure of how high this final column here is. And I'm just gonna copy and paste it in. Here's one of it, two of it, three of it, five of it, six of it, maybe 6.5. Let's say 6.5. Yeah, 6.5. Close enough. So actually, 1, 2, 3, 4, 5, 5.5. So from this rough measurement, what I can say is that V initial divided by V final is about 5.5. So with that in mind, these are the equations that I need to use. The ideal gas law, PV is equal to NKBT. And in your textbook, there's an adiabatic process formula, which says this quantity is constant. P times V raised to gamma is constant. And you kind of have to know the expression for gamma. Or do I have it memorized? Information, so yeah, diatomic ideal gas. I want to say for diatomic, gamma is 7/5, but I'm not 100% sure. So let me make use of the fact that this is an open book assessment. So I can look in the textbook to make sure that I remember the location of gamma correctly, and then I remember the gamma correctly. There's no shame in looking it up, just to be sure. It's been a while since I looked at it. I probably should have studied ahead to make sure I don't make mistakes and that I'll remember. It ought to be in the section adiabatic processes for ideal gas. And it should have this adiabatic expression. Yeah, all of that. Yeah, PV gamma is constant, good. And gamma is equal to what? It's not telling me what gamma is. Well, it's a Cp over Cv, so I can go look up the specific heat capacities of ideal gas. Heat capacities of an ideal gas. And I think there's either a table or something I can look up. So diatomic, Cp is 7/2, yeah. Cv is 5/2, so ratio 7/5, yeah. Good I should have trusted my memory. So with these equations in hand, this is what we can do. We can say so we are given the initial pressure, so P naught, 100 kilopascal times V is equal to N kb T initial, which will be 300 K. And now we work out the final expressions, P final, which we don't know, times V final, which we don't know, is equal to NKB T final, which we don't know. But this is where the adiabatic expression comes in. So what we can do is we can express we can let me just do it the long way, not using any shortcuts. So we are trying to solve for T final. This is the one unknown we are trying to solve for, and we and this is an information we have from the picture. So as a first step in eliminating unknowns, we can eliminate V final by rewriting this as V final is equal to V initial divided by 5.5. So putting that in, I can have this expression, P final times V initial, which for, let's say V initial divided by 5.5 is equal to NKB T final. Still not good because we don't know V initial. Although we can figure out V initial from here, I guess, kinda. But what I want to do is more of I want to use the adiabatic process equation. So let's see. So let's write this out explicitly. Explicitly, it would look like P naught V naught gamma is equal to V initial gamma is equal to P final V final gamma. And from here, we could solve for P final. Yeah, so let's solve for P final, which will be P initial times V initial divided by V final raised to gamma. And this ratio I already know. It's 5.5. So it's a P naught times 5.5 raised to gamma. So I can plug in this P final into here, and I feel like I still have to deal with the V initial, but I think I can do it. So I think I'm doing this much longer way than I had to because I'm a little bit disorganized, but let's just finish it up within the time limit, and that's really what counts. So plugging in P final, it's a P naught times 5.5 raised to gamma times V initial divided by 5.5, so I can do gamma minus 1 in the powers. Is equal to NKB T final. And let me have this expression for V initial. V initial was NKB T initial divided by P initial. So I can plug that in. Oh, P initial cancels out, I think. Yeah, I don't even need a P initial. So plugging this in, the whole equation, I have P naught times 5.5 raised to gamma minus 1 times V initial, and KB T naught divided by P naught is equal to N KB T final. Let's cancel out a whole bunch of stuff. And KB P naught, And that's it. T final is simply T initial times 5.5, the compression factor raised to gamma minus 1. This might have been derived in the textbook. So, okay, so let's do this. 300 Kelvin raised to power times 5.5 raised to power of 7 over 5 minus 1. That should be 593 Kelvin. Yeah, that's hot enough to ignite paper or cotton or whatever that combustible material. 5. Oh, I should have been watching time. That was supposed to be 5. I ran out of time while entering answer to C. It should have been 593 Kelvin. Come on. I'll bring the answer key over so that you can confirm that I was right. Sorry, I shouldn't have been so disorganized. Let me paste in my answers and then we'll be done here. I should have been watching time. I thought somehow thought I don't know. I saw that 9 minutes and then I think after that actually this doesn't work. After that somehow I was stuck there. I didn't run the timer in my head how much of the 9 minutes I spent. Alright. Let's paste this in. And then, so I'll save work and continue. So I should have gotten, oh, it's got 1, 2, 3, 4, 5, 6, 7, 8 parts, of which I got 6 right. So, I don't know, is that 3/4? 75%? Yeah, good. And let me go into instructor mode and bring in that screen so that I can show you the answer key for part C and demonstrate that yes, I didn't miss it. I just ran out of time to finish plugging in my answer. So test student, there it is. Yeah, correct, and here 593. Oh, why was it off? It might be a matter of this number being used. So I should have really just put in 590. That probably would have been graded as correct. So. Anyways, so that's it. So hopefully this is helpful. Thank you so much to those of you staying till the end. I will. Oh, there's no next time. So have a good winter break. Bye.